In this video, I'll be demonstrating how to create cross-sections from supplied data from various sources. This is a CAD file that was supplied, and in it contains a variety of information, including point data, contours, tin lines, and various other entities. First thing that I want to do is analyze this data and see what it is I have before I just blindly move into creating surfaces. But what I ultimately am going to do is create an existing surface followed by an as-built surface, cut cross sections, and calculate quantities. So let's take a look at this data. One of the greatest tools that I like to use is the Drawing Inspector. I turn on Drawing Inspector, which is basically a toggle. It turns on and off. So immediately it doesn't appear that anything's happening, but it is. If you just right click, you'll see a menu of all the things you can display as you hover over an entity. So I'm going to turn on the layer name and the elevation, not the rest of this information. So that's fine. And then I can hover over data such as these contour lines, and it displays the elevation of the contour line and the layer that it's on. I see we have E-contour, intermediate, and index. So those are the existing contour lines. Inside of that, I see a tin line, and these triangulation lines are also elevated. A point data, which is not elevated, however, it does have a tagged elevation, so Carlson would use that as well. I have some other perimeter lines that at 0 elevations. So knowing how Carlson works, that it's going to ignore things at a 0 elevation and take whatever is elevated and include that in the surface model, I know that I can use these entities as they are. I also see other contour lines in here on an as-built layer that are also elevated. These were actually created from a drone survey, whereas the existing contours were created from point data, an actual field survey. So I'm going to approach those two surfaces slightly different. Ultimately, it uses the same programming, but I'm going to evaluate them in a different manner. I see other point data in here. We have a center line of a road that is going to serve as the baseline for our cross sections. I believe these are right and left edges of the roadway that are elevated. I can tell by looking at the elevations. The left side looks reasonable compared to the as-built contour. However, the right-hand side is considerably off. 400 or 500 feet, it looks to me like. So I may have an issue with that has to be resolved. Another way to take a good look at this data, and it's another thing I like to do in the very beginning, is I like to twist this up in 3D so I can actually see the data. One of the tools that I like for that is Orbit or Real-Time Sphere, which work very similar to each other, but you can just click and rotate in 3D the data. By doing that, I can immediately see some issues. That, in fact, is the right-hand side of the trail that I was talking about, and it is elevated inappropriately. They also have these spikes, these red lines coming up and down that are going in and out of the data. Those will cause problems with the surface model. And then I can see some spikes here. I hover over one of these, it is the as-built contour. So I had mentioned those are drone contours, so those are likely trees that were not stripped out of the drone data. So we have contours running up the height of a tree. So that will have to be dealt with. You can actually edit these in this view, which I'm going to do some of that, but I'm going to start by isolating some of these layers and see which ones have the issues, which ones I can use, and minimize the amount of editing that I have to do before I can get started. So I'm going to use my isolate layer routine, and I'm going to pick one of these contour lines. So this is an existing contour. In my layer manager, what might be a little bit easier to do, I'm going to turn on the index So I can see that my existing contours look very reasonable. I also want to take a look at those tin lines. I believe those were on a layer called triangulation lines. And I'm going to turn those on. Those follow right along the contour lines. So those to me look like they are pretty reasonable. Turning all my layers back on. These lines are called tie-in lines. I'm not sure what the purpose of those are for, but I know that they will introduce bad data into my surface model. So I can either just simply not use them, or I could correct them. I'm going to go ahead and clean some of that up. I will use a command under Edit called 3D Entity to 2D. Command line prompts what elevation I want it to be. It's 0. And I'm just going to use a fence for selection and draw a line through here. It selects all those spikes, and when I hit Enter, they are all changed to 0. So that eliminates a lot of the data out of there. I am now also going to try to clean up these contour lines on the as-built contour layer. So I'm going to isolate that layer and take a look at those spikes. So using my 3D orbit and rotating carefully, I can actually select some of this data and eliminate those contour lines, because I'm going to be building the surface model out of the contour lines themselves for the as-built contours. I have no other data in which to do that. So I'm going to at least try to eliminate the majority of these spikes to improve the quality of my surface model. So I'm simply just going to erase, and using a window polyline for selection, I can window these in. And I'm going to turn off my drawing inspector during this process. I'm going to spend a couple minutes here. In some cases like this, you have to be very careful about selecting. If I was to select too much here, I'd be erasing good contour lines. So I've got to be very careful about flipping up my perspective to make sure I'm not over-selecting or under-selecting data. Once I've completed editing these contours and eliminating data as best as I can, thaw all my layers again. The other thing I can do is either change or move this line. I'm not real sure of the data change that created this particular line to be out of line with the rest of it, so it's off maybe 500 feet. So I'm just going to simply not use that line. So when I completed my editing process, I am going to go back to under the 3D view, hit Plan View, and it returns you back to this perspective. So I'm going to start with the existing surface model to build that. I can look at this and see that the tin lines, I've already determined actually that the tin lines and the contour lines are pretty much coincidental with each other, so those look to be pretty good data. So I'm going to simply build the surface model out of the tin lines. So I isolate that layer. And there are my tin lines. So now I go into the surface model, and I'm just going to triangulate and contour. I have Write Tin File on. I'm going to hit Select, and it will create a new one. These are the existing, so I'm just going to call it Existing. Under the Contour tab, I don't really want it to draw contours, so I'm going to turn that off. I certainly don't want contours labeled. I'm just going to check my selection set. They're all grayed out right now, and if I click this box for selecting the options, I can determine and verify that I have 2D polylines, which are contour lines, and 3D polylines, which are those tin lines. So all my selections are in there. Ignore zero elevations, as you can see, is the default. Inclusion-exclusion areas is there so you can create a boundary if you want as an inclusion area, and then you could have separate polylines as exclusion areas. I am not really going to worry about that. I'm going to instead allow it to shrink wrap the perimeter, which essentially makes a boundary line invisible to you. The process, by selecting it, it creates a shrink wrap entity, which is another Carlson command that draws a polyline around the outside of the entities. Well, it's going to use that as the boundary with 3 options, low, medium, or high, which dictate how tight it follows that boundary. So I'm going to leave that on low, and all I have to do is hit OK now, and I will window in those tin lines. So it quickly made the existing surface. Thaw these layers again. Now for the as-built surface model, the only data I really have is these contours developed by the drone survey, which I've done my best to edit. So I'm going to isolate that layer. Essentially do the same thing. Just going to create a surface model. Triangulate and contour. Create another tin. This one I'm going to call as built. All the rest of the settings are the same. Just window this in and enter. In this case, I found some errors in here. Crossing break lines. This shows the elevation error of each crossing break line. Those are large enough there that I am going to concern myself with them. Some of these smaller ones aren't a big deal, but that's 3/4 of a foot. So I'm going to highlight one and just hit zoom in a few times until I find it. And right there I see that there is a line that is crossing over the contours. So I'm just going to erase that and quickly look and see if there's any more of those. They highlight. I see one on the other side here, so I'm going to zoom into that. Same situation. There are some lines there, so I'm going to erase that and exit. And we'll just try that again. Say yes to override that, and that time no error. Turn all my layers back on. Now I want to establish this alignment. But to make my life easier, I'm going to freeze some of these layers now that I don't need. I don't really need to look at the contours or the point data. I find other point data in here that appears to be a calculated layout. So I'm going to get rid of that, remembering that this layer, or this side of the roadway, had errors. I'm going to freeze that as well. So I've got my layers set up. I'm going to define the center line, the baseline of this project. I have a polyline that's drawn in here. It looks like it's continuous from beginning to end. I'm going to check, though, the stationing on it is labeled here at every 50 feet plus some odd intervals. So I just want to check and make sure that this is the beginning station of 0, 0. So I'm just going to inverse from the intersection at 1 plus 0, 0 to the beginning. And I see it's not exactly 100 feet, 98.366. So that means the beginning of this is actually 1 foot, 0.633, and not 0. So I need to keep that in mind when I create my center line, which is the next step here. So I'm going to go under Create Polyline to Centerline File. So it's going to take that polyline that's already drawn and write it out to a .cl file. I will name that CL Road. Select that polyline. You see briefly that there's arrows showing the direction of the polyline. The stations are ascending based upon the way it was drawn. If it was incorrect, you have an option to reverse it at this point. It defaults to the beginning of 0 plus 0, 0, which we realize is not quite correct. So we're going to put in station 1.633, and that defines our station. Verify that by using this command, calculate offsets. Make sure that I'm defining the centerline by the centerline file. I hit OK. Grab that centerline file. You see a little display of that. And I hit open, and as I move my cursor around, you can see in the dialog box above that the station is changing as I move through. So I'm just going to kind of go up here to the end and pick an even station here at 30 plus 0, 0, and we're within 0.03 of a foot, so that's going to be good enough. I'll double check the end station, 30 plus 38.79, so that's good. Let's get out of that command. But when you issue this command, it does create a report of any points that you ID'd, and you can print those out if you wanted to. Now what I'm going to do is define a cross-section layout. I'm going to go into my sections menu. And this is somewhat of a two-step process. First thing I'm going to do is we're going to input edit a section alignment. What that does is define the alignment of the sections that we're going to take. The section alignment is basically giving it the horizontal alignment, the width of the cross-section sampling, and the frequency of the samples. I'm going to go into sections and input section alignment, and this creates an MXS file which contains the alignment parameters. It's asking me to identify the center line. We already have the center line file created, so I'm going to hit F for File and select the center line file again. Then we enter in the station interval. We want them every 50 feet, and the left and right offsets. So I'm going to leave them at 100, even though it's more than what I need. If it exceeds the surface model's parameters, then it will just stop. Then you have other options in here about prompting and adding additional stations, special stations like on profiles, PVC, PPT, etc. I'm not going to concern myself with those, so I'm just going to hit OK, and that sets up the alignment. You can see temporarily on the screen colored lines drawn along that sample line. So those are where the cross sections will be sampled. You also have a dialog box that shows up that allows you to edit this MXS file, this alignment file, as you see fit. So we hit save and exit, and that portion is done. The next step is to actually sample from that MXS file. So we're going to create the cross sections from a grid or tin surface. So this is first selecting the tin surface that we're going to sample from, and we're going to start with the existing tin. Link sections to the triangulation. That linking means that if we were to update the tin file for whatever reason, the cross sections would update with it as well. I'm going to set that to prompt. I don't anticipate that we'll be doing that, but just in case. So I'll hit OK. And then it's asking me to select the MXS file to process, which is the one we had just created. The next prompt is asking us to create a section file. I'm going to name it Centerline Road. I'm going to repeat that process, creating sections from a tin file. This time I'm going to pick the as-built tin, but using the same MXS file and writing out CL as built. Now, if we want to look at those files, we can now go into Input Edit Section File. So I'm going to start by looking at the as-built, open that up, and then you see an option for a reference section. I'm going to put in the original CL Road file. I can look on these now and I can compare the cross sections, and by using the next button I can just go through one at a time and compare the cross sections between the as-built and the original files. Now you can, if you want to, actually edit these. You can see that there's points not tying in exactly correct. They're at the exact same position, keeping in mind that we have an vertical exaggeration of fit. If we lowered that to say just a ×2 or something, we'll see those a little tighter than what it appeared before. I like them on fit just so I can see the whole thing. So I'm going to close out that and exit that for now. Now that we've created and reviewed the cross sections, we're ready to print them. So we'll go back into sections and execute draw a section file. This dialog box pops up and we can add cross section. So I'm going to add the existing cross section first and add the as-built cross sections second. The order of these will become apparent in the next step. And then when I hit OK. So here's the dialog box for setting up drawing the cross sections. So the first thing I'm going to do is pay attention to the horizontal and vertical scale. So these are set to 40 and 4, which I'm going to leave. It's a 10 times vertical exaggeration. I am going to pick sheet plot, which means it's going to attempt to place cross sections based upon the sheet size. I'm still going to do that right here in model space in my drawing, as opposed to a vertical stack where they would all be on top of each other or manually picking each location. Now, to set the defaults, to find the minimum and maximum heights and the widths of the cross sections and such, we execute the scan file to set defaults button. And then it asks if we want to set sheet numbers of rows and columns. I'm going to say yes. So it scans the file and it puts in a minimum and maximum elevation, the station range, and it sets up the defaults for the sheets as we're going to plot them. I'm going to draw all the stations. So if you only wanted to draw some, you would simply put that on selected. I'm going to leave these defaults alone. These have to do with how each cross-section is going to lay out on the sheet. Now there are several options of what to label as you're drawing the cross-sections. The ones of note are label volumes and label end areas. So if I turn those on, it will actually do an average end area calculation from the cross-sections, which if you have good cross-section data and you are required to produce a report like that, that would work out well. It will place an accumulative volume on each cross-section, and you have an option to label running total volumes as you go. It's a more accurate option to calculate volumes using the two-surface method, which essentially compares one tin surface to the other. So we already have those tin surfaces created. I'm going to calculate volumes using that method instead. So the next thing I'm going to do is take a look at the grid setup. So this is to draw a grid for each cross section. You can set your layers and text sizes, but the main thing that I want to check is right here, my horizontal and vertical grid spacing. So I have those set to put a grid every 50 feet horizontally and every 5 feet. That should coincide with the vertical exaggeration that I'm using. The next thing I'm going to take a look at is the layers. So the order of those section files that I brought in coincide here. So the layer that it's going to draw the existing is on a layer called existing, and the as-built is going to be on one called final. We didn't define any subgrades, so that will not be plotted. So when I have all my settings ready to go, I hit OK. So the sheet drawing parameter dialog box pops up. So this would not happen if I were using another method as vertical or picked. So I'm going to go ahead and plot these in model space. So they're just going to be off to the side instead of, say, creating layout tabs. This block name is a standard sheet that's set up. The expectation is that you will modify that sheet with your own title block and whatever other information you would want on a standard cross-sections sheet. But this is just the default sheet block. This is the size of the paper, including the borders, sheet layer. Then we have an option for rows and columns of the cross-sections. These values are in here from this cross-section scan that we had performed earlier. So this was going to plot them out with just one row and 5 columns. I'm going to force that to tighten that up a little bit by putting 2 rows per sheet. Once these values are all set, we just hit OK. And then it asks where you would like to begin plotting these, and I'm just going to pick a spot on the screen off to the side. So the program draws all the sheets with the cross sections at the scales provided. So I had mentioned earlier calculating volumes by the surface model method. So under surface, you have volumes by triangulation. I'm going to use the 2 triangulation surface volumes. So it asks for the existing surface, which is called existing, and the final surface, which is the as-built. It is now asking for an inclusion polyline. In this case, I am going to select the boundary line that had been drawn around the as-built contours. So I simply pick that polyline, hit enter. It's now asking for an exclusion polyline, which I do not have, so I just hit enter. There's an option for cut and fill shrink factors. I'm not going to take those. I am just going to hit OK. And there's a report with my volumes. I can plot this in the drawing file by hitting Screen, mText, and off to the side I have my report with volumes.